In June of 2017, in a paper buried inside the Astrophysical Journal Letters that almost no one outside of exoplanet astronomy noticed at the time, a postdoctoral researcher at the Massachusetts Institute of Technology named Kishore Patra and his collaborators announced something that had never been measured before: the slow death of a planet in real time. The planet is called WASP-12b. It is a gas giant larger and warmer than Jupiter, orbiting a yellow star a little brighter than our own Sun in the constellation Auriga, about 870 light-years from Earth. Its orbit is shrinking. Every year the planet completes its lap around its star a tiny fraction of a second sooner than the year before. The number is about 29 milliseconds per year. Not 29 seconds, not 29 minutes, 29 thousandths of 1 single second. That number on any human reference is invisible. You could not measure it with a wristwatch. You could not feel it. You could not, sitting on the surface of any other planet, tell from one orbit to the next that anything had changed. But on the scale of a planet's lifetime, it is an avalanche. It means that WASP-12b slowly, steadily, lap by lap, is falling toward its Sun. And as it falls, the star is pulling its atmosphere apart, swallowing it mile by mile, in a process that we are watching in real time from across most of 1,000 light-years away. The planet is being eaten. If you find that as fascinating as I do, hit subscribe. Pour yourself something warm, get comfortable and settle in, because tonight we are going to walk slowly through the strange and quietly beautiful story of a world that is dying, of a star that is consuming it, and of what its long, patient end has to teach us about our own. Part 1. The planet that should not exist. When astronomers first found WASP-12b in 2008, almost nothing about it made sense. The discovery was made by an English astronomer named Leslie Hebb, working with a wide-field survey called Super-WASP, the Wide-Angle Search for Planets. Super-WASP was, by the standards of professional astronomy, a small project. 2 robotic observatories, one in the Canary Islands and one in South Africa, each made up of an array of small wide-field cameras, lenses about the size of a grapefruit, that pointed at large patches of sky every clear night and recorded the brightness of every star in the field. The cameras were not sophisticated. The data was not, by the standards of a flagship telescope, especially good. But there were a lot of stars in the field, hundreds of thousands of them, every night. And the project was looking very patiently for the same thing Kepler would later look for: shadows. The shadows of planets transiting their stars. In 2008, in the constellation Auriga, the Super-WASP cameras picked up a transit. A small dip in the brightness of a yellow star designated WASP-12, lasting about 3 hours, repeating every 26 hours and a few minutes. The dip was deep, about 1.5% of the star's light. That was a strong signal. Whatever was passing in front of the star was, in proportion, very large. When the follow-up measurements came in, the size of the planet was confirmed. WASP-12b is roughly 1 4/10 times the mass of Jupiter, but it is 1 8/10 times Jupiter's diameter. That, to anyone who studies these things, was already strange. A planet that is heavier than Jupiter should be, very roughly, the same size as Jupiter, or smaller. Mass should compress the body inward. Gravity should pull the gas down on itself. WASP-12b is bigger than it should be. It is, in the language of planetary science, inflated. There is one easy explanation for an inflated gas giant: heat. If you take a Jupiter-sized planet and you put it very close to its star, the upper layers of the atmosphere absorb so much energy that they puff outward, and the planet to an outside observer looks larger than it would if it were colder. But heat alone is, in fact, not quite enough to explain the inflation of WASP-12b, or of most of the dozens of other inflated hot Jupiters that have been catalogued over the past 20 years. The numbers do not quite work. If you simply heat a gas giant, the upper atmosphere expands for a while, but the planet's interior, deeper down, is not significantly affected, and the total radius increase is more modest than what we actually measure. WASP-12b is too big, by a meaningful amount, even after you account for direct surface heating. There must be, the models suggest, some mechanism that is depositing energy deep inside the planet, where it can heat the bulk of the body and inflate it from within. Several candidate mechanisms have been proposed. Tidal heating, the friction generated by the constant deformation of the planet's body in its tidal stretching. Ohmic heating, the resistance generated when ionized winds in the upper atmosphere flow through the planet's magnetic field. Some combination of the two. Almost certainly, both contribute. The exact balance is still being worked out. What this means for our story is that WASP-12b is not just a planet in a bad neighborhood, it is a planet whose own internal physics, the very mechanism that holds it together against the pull of the star, is in some sense already failing. The body is being heated from outside by the star and from inside by the work that the tides are doing on its own structure. Both heat sources in different ways are loosening the planet's grip on itself. WASP-12b is very, very close to its star, so close that its orbital period, which is the length of its year, is 1 Earth day and a few minutes, less than 26 hours. The planet is, in cosmic terms, almost touching the surface of its sun. The day side of the planet, the side permanently facing the star, sits at a temperature of about 2,500 degrees Celsius. At that temperature, almost any solid you can think of melts. Iron melts, glass melts, stone melts. The whole upper atmosphere of the planet is, in a real sense, vaporized. That alone would make WASP-12b a curiosity, but the inflation and the proximity were only the first strange thing about it. The next strange thing was the shape. Most planets are very nearly spheres. Gravity is a force that pulls equally in every direction toward the center of the body, and, given enough time, anything large enough to have noticeable gravity rounds itself off into a ball. The Earth is a ball. Jupiter is a ball. Every planet you have ever seen a picture of is a ball. WASP-12b is not a ball. WASP-12b is shaped, more accurately, like an egg. A long, oblong, stretched body, with one end pointing at its star and the other end pointing away. The reason is that it is so close to its sun that the gravitational pull of the star itself on the near side of the planet is nearly as strong as the planet's own gravity. The two forces, almost equal, deform the planet into a teardrop. The body is being stretched. It does not look like a planet. It looks like something that is being held in two hands, very slowly, and pulled. That is what we knew about WASP-12b within 2 years of its discovery. A hot Jupiter, larger than it should be, in an orbit that takes barely a day, shaped like an egg, with a surface so hot that nothing solid could exist there. By the standards of the early days of exoplanet astronomy, when a hot Jupiter was already an exotic find, WASP-12b was already strange. But it was about to get stranger. Part 2. The cameras that found it. Before we go further, it is worth understanding very briefly the kind of project that found WASP-12b in the first place, because it tells you something about the temperament of this entire field. The SuperWasp project did not have the budget of a flagship space mission. It did not have the prestige of the Hubble Space Telescope. It had a few £100,000, 2 small observatories, and a small team of astronomers spread across several British and South African universities. The lead scientist on the survey, an astrophysicist named Don Polacco at Queen's University Belfast, had spent years arguing for it against funding panels who, much like the ones William Barucki had faced for Kepler in the United States, kept saying the technology was not ready, the science was not strong enough, the chances of finding anything significant were too low. Polacco kept arguing. The funding came through, the cameras went up, they started taking pictures. The technique SuperWasp used is the same one Kepler would later use on a much larger scale, the transit method. When a planet passes in front of its star, from your point of view, the star dims by a tiny amount. The amount of the dimming is proportional to the area of the planet relative to the area of the star. For a planet the size of Jupiter passing in front of a sun-like star, the dimming is about 1%. For a planet the size of Earth, about 1 part in 10,000. SuperWasp, with its small cameras, could only see the bigger dips. It was good at hot Jupiters. It was not good at the time at smaller planets, so it found dozens of hot Jupiters very efficiently in the first few years of its operation, and then handed those candidates off to bigger telescopes for confirmation. WASP-12b was the 12th confirmed planet from the project, which is what gives it its name, the 12 in the designation. The little b by convention means the first planet around the star. Here is the detail that often gets lost. Almost everything we know now about WASP-12b, the egg shape, the mass loss, the orbital decay, the slow consumption, depends on that initial detection by a small array of grapefruit-sized cameras in 2008. Without that detection, the planet would have remained, as far as we are concerned, invisible. The light from WASP-12 would still be reaching Earth every night. The transits would still be happening every 26 hours. The whole story would still be unfolding. We just would not know about any of it. We would be looking at the same patch of Auriga on a clear winter evening and seeing a faint yellowish star, and not knowing that one of its planets was being eaten alive. That is the thing about astronomy. The stars are not hiding. The chemistry is not hiding. The orbital decay is not hiding. The information has been arriving on Earth for as long as the planet has existed. The only thing that has ever been missing is the instrument capable of reading it. WASP-12b in 1995, before SuperWasp existed, was already losing its atmosphere at the same rate it is losing it now. We just did not have the cameras. The information was there. The reading was not. In 2008, the reading began. There is a small irony in how astronomy works that is worth noting before we move on. The discovery of WASP-12b was not, on the day it happened, treated as historic. It was the 12th confirmed planet from a single survey in a year when planets were already being found at a rate of dozens per year by SuperWasp and several other ground-based surveys, and when Kepler's launch a few months later was about to flood the field with thousands more candidates. Within the small community of exoplanet researchers, WASP-12b was, on its discovery, just another hot Jupiter, a particularly large and hot one, true, with an unusually short orbital period, true, but not, by any measure that mattered to most astronomers in 2008, a remarkable object. The papers that described it were not on any major journal's cover. The press releases were modest. Most working astronomers, looking at the same year's discoveries, would not have picked WASP-12b out of the catalogue as anything special. It became special slowly. The discovery of the egg shape in 2010 by an astronomer named Shu-Lin Lee, working at Peking University, who modelled the tidal distortion of the planet's body from the transit light curve and showed that no spherical model could fit the observations. The atmospheric mass loss measurement in 2013 by Carol Haswell and her collaborators using Hubble's UV spectrograph, which showed that the planet was losing material into space. The orbital decay confirmation in 2017 by Kishore Patra at MIT, which made the planet the first ever caught in the act of falling. Each step, individually, was a small advance. Each step depended on the previous one. Each step was made by a different team in a different country, with different instruments, and was published in different journals. None of them was, on its own, world-changing. All of them, together, were. Each of these results, on its own, was a minor finding inside a larger conversation. Together, over a decade, they made WASP-12b the most carefully studied dying planet in human history. But the cumulative status was not visible at any single moment. It was visible only in retrospect, by looking back over the body of work and noticing that one specific planet had become, almost without anybody planning it, the test case for an entire branch of theoretical work. That is the way most important discoveries actually happen. Not in a single dramatic announcement, but in a slow accumulation of small results by many different groups over a span of years, until at some point somebody steps back and notices that, taken together, the results add up to something none of them on their own would have suggested. WASP-12b was not, in 2008, the planet whose death we would be measuring 15 years later. It became that planet, slowly, as the data accumulated. There is a thought that I keep coming back to when I read the early SuperWASP papers, which is that almost everybody involved with the project in the first few years was working at the limits of what the equipment could do. The cameras were small, the pixel scales were coarse, the atmospheric noise on a ground-based observatory was constantly threatening to drown out the signal. The data reduction pipelines had to be invented as the data came in, because no one had ever tried to do photometry at this scale before on this kind of equipment. The team was at any given moment 3 or 4 years away from the next generation of instruments that would do the same job better. They knew it. They worked anyway. The hot Jupiters they found in the years before Kepler arrived and changed everything are the foundation of an entire branch of modern astronomy. They were found by people who did not have the budget to wait for the better instrument. That, more than anything else, is the temperament of the field. The work is done by people who are not waiting. They are building the instruments they have available and pointing them at the sky and sending the data into the slow, systematic accumulation, and then they are dying, in the human sense, before the questions they helped open are finally answered. Don Polacco was 43 when WASP-12b was discovered. Whether he will live to see the planet's death or even to see the orbital decay measurements push past the 5 sigma threshold of formal confirmation is a function of his personal lifespan and the planet's 3 million year clock. The planet does not care. The work was done. That, in some sense, is the only honest way to explain why anybody does this kind of astronomy at all. Part 3. A year that lasts a day. To understand what happens to a planet that close to its star, you have to spend a moment with the orbit itself, because almost nothing about it lines up with the kind of orbits we are used to. In our own solar system, the closest planet to the Sun is Mercury. Mercury's year is 88 Earth days. That is, by every textbook of planetary science you have ever opened, the example of a fast, hot, tightly bound orbit. Mercury sits about 36 million miles from the Sun. The day side of Mercury, when the Sun is overhead, reaches about 430 degrees Celsius. By the standards of our own neighbourhood, Mercury is the inferno. WASP-12b's year is just over 26 hours, not 26 days, not 88 days, 26 hours. Less than a single rotation of the Earth. That is roughly 80 times faster than Mercury's orbit. The planet sits about 2 million miles from its star, which is, very roughly, 20 times closer than Mercury is to the Sun. And the day-side temperature, the side that permanently faces its star, sits at around 2,500 degrees Celsius, 6 times hotter than Mercury at noon, a temperature at which most rocks vaporize. There is no equivalent of this in our own solar system. There is no orbital geometry anywhere within 1 billion miles of our own Sun that resembles what WASP-12b is doing. The closest analogy is something like the inside of a kiln, a high-temperature industrial furnace, held at the temperature where steel becomes a glowing liquid. WASP-12b is a planet that lives permanently inside that kiln. Because the orbit is so close and because gas giants like WASP-12b have very low densities, the entire planet is, in a real sense, vulnerable. It does not have a hard surface. It does not have rock or iron. It has clouds, increasingly compressed as you go down until they merge into a hot, dense fluid of mostly hydrogen and helium, and somewhere very deep, possibly a small core of heavy elements. But for our purposes, the planet is essentially a ball of hot gas. A ball of hot gas under enormous gravitational stress. A ball of hot gas being held in two hands by its own gravity and by the gravity of its sun, and slowly pulled. There is one consequence of the close orbit that is worth pausing on, because it is going to matter for everything that comes next. The orbit is so tight that WASP-12b is tidally locked to its star. One side of the planet permanently faces the Sun. The other side permanently faces away. There is no day and night cycle on WASP-12b. There is the day side and the night side and a thin strip in between called the terminator, where the day meets the night. The day side is 2,500 degrees. The night side is much cooler, perhaps 1,000 degrees, perhaps less, depending on how efficiently the atmosphere transports heat from one side to the other. This temperature difference matters because it drives enormous winds. Models suggest that the upper atmosphere of WASP-12b is moving from the day side toward the night side at speeds of several thousand miles per hour, redistributing heat in a permanent global gale. The whole gas and envelope of the planet is in motion all the time, dragged from the hot side to the cool side, blown back around by Coriolis forces, never settling into anything you could call a calm day. The planet is, on every scale, in constant turbulence, and from across most of 1,000 light-years away on a clear winter night in the constellation Auriga, that turbulent, distorted, perpetually vaporizing body crosses in front of its star every 26 hours and dims it by 1.5% for about 3 hours at a time, like clockwork. If you wanted, in some hypothetical way that no engineering project in the foreseeable future will allow, to send a probe to WASP-12b, the journey would not be the simple matter that science fiction usually imagines. 870 light-years at the speed of the fastest spacecraft we have ever built which is the Parker Solar Probe at its closest approach to the Sun, would take roughly 15 million years. That is twice the time since modern humans appeared. Even at 1/10 of the speed of light, which is far beyond anything we currently know how to build, the trip would still take 8,700 years. By the time the probe arrived, the planet would have lost a measurable fraction of its remaining atmosphere. The probe's onboard data, when it began transmitting back, would describe a planet slightly different from the one that left Earth's solar system. The orbit would be slightly tighter, the atmosphere would be slightly thinner. The world the probe arrived at would not be the world it had been built to study. That distance, in other words, is not really a distance at all in any human sense. It is a buffer, a guarantee that the planet's life and our own life will never overlap in any direct way. We can watch, we can measure, we can point our most sensitive instruments at it and pull in its photons one at a time and assemble them into a story, but we cannot visit. We cannot interfere. We cannot, even if we wanted to, slow the falling. The eating, in this sense, is happening behind a kind of glass. We can see it. We cannot reach in. There is something almost peaceful about that when you sit with it. Most of the things that happen in your life, you are expected to do something about. The phone rings, you answer it. The email arrives, you reply to it. The problem at work surfaces, you fix it. Almost every act of attention in an ordinary day comes with an implied call to action. The eating of WASP-12b does not come with one. There is no action available, there is no fix. There is only watching and measuring and writing the data down and passing it forward to whatever future generation will use it to refine the model. The work is purely observational. The action, in any conventional sense, is something the universe is doing on its own. That kind of work is, I think, increasingly rare in modern life. Almost everything else asks something of you. The night sky, when you look at it carefully, asks nothing. It just is. The eating just is. The orbit just shrinks. The atmosphere just falls. None of it depends on you. None of it depends on whether anybody, anywhere, is paying attention. The universe does its thing on its own schedule, in its own way, and the most we can ever do, looking up at it, is to notice. That is also enough. Part 4. The shape of a planet under pressure. The egg shape of WASP-12b is not a guess, it is a calculation, and the calculation goes back almost 200 years. In 1849, a French astronomer named Edouard Roche worked out, on paper, what happens when one body orbits another at very close range. Roche was not thinking about hot Jupiters. He was thinking about moons. Specifically, he was thinking about the rings of Saturn, which had, by the 1840s, been studied for over 200 years, and which were a mystery. Why, asked Roche, do the rings sit where they sit? Why do they not, like every other moon in the solar system, accumulate into a single body? Why do they remain forever as a thin disk of small particles never coalescing? Roche's answer was a single elegant calculation. He worked out that, for any pair of bodies, there is a critical distance at which the larger body's gravity on the near side of the smaller body becomes stronger than the smaller body's own gravity holding itself together. Inside that distance, the smaller body is, very gently but very inexorably, pulled apart. It cannot maintain its shape. It cannot accumulate. The gravity of the larger object is winning every moment against the gravity of the smaller object. The result, if you bring two bodies inside this critical distance, is that the smaller one disintegrates. Roche's calculation gave a specific formula for this distance in terms of the masses of the two bodies and their densities. The distance is called the Roche limit. It explains beautifully why Saturn's rings exist where they do. The rings sit inside Saturn's Roche limit. Any moon that strayed inside that limit in the deep history of the solar system was pulled apart, and the debris spread out into a disk. The disks we see today are the corpses of moons that came too close. Roche's paper sat in the literature very quietly for the better part of a century before its full implications were appreciated. His original interest was Saturn, and Saturn alone. He did not, in his own writing, anticipate that the same calculation would later apply to the rings of every other gas giant in our solar system, to the question of how the asteroid belt formed, to the question of why no large moons exist within a certain distance of any large planet, to the structure of binary star systems, to the disruption of small comets that pass too close to the Sun, and eventually to the slow death of hot Jupiters around other stars. The Roche limit, when it was generalized over the next 150 years, turned out to be one of those numbers that shows up again and again in places where the geometry of two bodies orbiting each other is part of the story. It is, by any reasonable measure, one of the more useful single equations in celestial mechanics. There is a small irony in the fact that Roche himself never saw the equation applied to anything outside our own solar system, because the existence of planets around other stars was, in his lifetime, not a confirmed fact. It would not be a confirmed fact for another 146 years until 1995. Roche died in 1883. The first exoplanet around a sun-like star was announced in 1995. Between his death and that announcement, 112 years of physics happened, none of which he was alive to read. The Roche limit in his time was a mathematical curiosity about the rings of Saturn. In our time, it is the boundary at which a hot Jupiter, 870 light-years away, begins to bleed. Here is the part that almost no one outside of celestial mechanics knows. WASP 12b sits very, very close to its own Roche limit. Not inside it, not yet, but close enough that the tidal stretching of its body is significant. The gravity of the star on the near side of the planet is meaningfully stronger than the planet's own gravity. The planet is being deformed every second by that asymmetric pull. The result is the egg shape. The atmosphere on the near side bulges outward toward the star. The atmosphere on the far side bulges outward in the opposite direction by a smaller amount because of how tidal forces actually work. The body of the planet in cross-section is shaped like a teardrop with a long axis pointing at the star. Modelling work, primarily by a team led by an astronomer named Carol Haswell at the Open University in the United Kingdom, showed in 2010 that the atmospheric distortion was so extreme that material on the near side of the planet was, very slowly, escaping the planet's gravity entirely. The bulge was not a stable feature. It was a leak. The very upper layers of the bulge were being pulled by the star's gravity, faster than the planet could pull them back, and they were escaping into space. Once material escapes the Roche limit, it does not come back. It cannot. The planet's gravity is too weak, the star's gravity is too strong, and the geometry is one way. The material is then in a slow, hot, drifting current, falling toward the star. Some of it strikes the star and is absorbed. Some of it forms a thin, diffuse disk around the star. Some of it spirals back through the planet's path on the next orbit, dispersing further. But once the atmosphere has crossed the Roche limit, it is, From the planet's point of view, gone. That is the first part of the eating. The atmosphere is being stripped off, layer by layer, every orbit, by the asymmetric pull of the star, 26 hours at a time, forever. Let that sit for a moment, forever, from the planet's point of view, until the eating is done. Then forever ends. There is, embedded in this picture, a question that bothers many people the first time they encounter it. If WASP-12b is losing atmosphere on every orbit, why has it not, by now, lost all of its atmosphere? It has been in this orbit, the best estimates suggest, for at least 1 billion years, possibly longer. 1 billion years of atmospheric loss, even at modest rates, should have stripped a planet of any reasonable atmosphere many times over. Why is there still anything left to bleed? The answer is partly that the loss rate at the start was much slower. The orbit was further out, the Roche limit was further from the planet, the tidal forces were weaker. As the orbit has decayed over the last 1 billion years, the loss rate has accelerated in a feedback loop until it has reached the value we measure today. Most of WASP-12b's life has been comparatively peaceful. The fast eating in cosmic terms is recent. The other part of the answer is that the planet was, when it formed, very large. Larger than Jupiter is now. The atmosphere that has been lost even at this rate is still only a small fraction of the total mass. WASP-12b is being eaten, but it is being eaten the way a glacier is melted by a warm spring. Slowly, in proportion to its size. The planet is doomed. The planet is also, on the timescale of any individual measurement, mostly intact. This is the unusual position that astronomy, very occasionally, finds. WASP-12b is dying. It is also, in real time, very much alive. Both statements are true. On the same evening, in the same data. Part 5. Here is where it begins to come apart. Here is where the story shifts. From the geometry of forces to the geometry of consequence. Because the mass loss from WASP-12b is not just a theoretical possibility. It is something we have, since 2013, been able to measure directly. The measurement was made by a team led, again, by Carol Haswell in collaboration with an astronomer named Luca Fossati, then at the Open University and now at the Austrian Academy of Sciences. They used the cosmic origin spectrograph on the Hubble Space Telescope to observe WASP-12 in ultraviolet light during a transit. The transit, in visible light, lasts about 3 hours and dims the star by 1.5%. In ultraviolet, the team predicted the transit would last longer and dim the star more because the planet's atmosphere, extending outward from its Roche limit bulge, would absorb more of the star's UV light than the planet's solid silhouette would block invisible light. If they were right, the UV transit would tell them very directly how much atmosphere was extended around the planet. They were right. The UV transit, when measured, lasted longer than the visible light transit and dimmed the star by significantly more. The planet, as observed in ultraviolet, looked roughly twice as large as it did in visible light. That meant there was a vast extended atmosphere around WASP-12b, reaching well beyond the visible disk of the planet, absorbing the ultraviolet light of the star. That cloud the team's modelling showed was the leak. It was atmosphere that had been pulled from the planet, was no longer gravitationally bound to it, and was, as observed, actively flowing toward the star. The shape of the cloud in their best fit models was asymmetric. It was elongated. It was a tail. A trailing stream of stripped atmosphere falling from the planet toward the star on every orbit, every 26 hours. Let that sit for a moment. We are watching. From across most of 1,000 light-years away, a planet bleed. The mass loss rate when the team did the calculation was somewhere in the range of 10 to the -7 Jupiter masses per year, which means roughly that every year WASP-12b is losing about a 10 millionth of its total mass to the star. That sounds tiny. In a sense it is. But integrated over the time scales of a planetary system, the numbers add up. At the current rate, the planet would lose all of its atmosphere in roughly 10 million years. But the rate is not constant. As the planet falls closer to its star, the Roche limit shifts, the tidal forces strengthen, and the stripping accelerates. The eating, in other words, gets faster the more the planet is eaten. Here is the analogy that I find most useful when I try to picture this in my own mind. Imagine a slow ice cube dropped into a glass of warm water. At first, the melting is slow. The surface of the cube is cold. The warm water is in contact with only a small area, and the heat transfer is moderate. As the cube melts, the surface area in contact with the warm water increases. The cube becomes more porous and more vulnerable, and the rate of melting accelerates. The last fragment of the cube melts much more quickly than the first chunk. The death of a cube of ice in warm water is not linear, it is exponential, slow, then faster, then suddenly all gone. WASP-12b in this picture is the cube. The star is the warm water. The eating is the melting. The rate today is what it is. The rate in 1 million years will be many times higher. The rate in 2.5 million years will be higher still. The final fall of the planet, when the spiral becomes very tight, will happen in a small fraction of the total 3 million year window. Most of the timeline is spent in the slow, almost imperceptible early phase. The dramatic part, when the body really comes apart, is the very last act. Here is the thing that I want you to sit with for a moment. WASP-12b, on the night you are listening to this, is in the slow phase. The orbital decay is real but small. The atmospheric loss is real but limited. The body of the planet is, for all the talk of dying, mostly intact. It still has, by mass, more than 99% of what it ever had. It still looks from the outside more or less like a hot Jupiter that happens to be a little stretched. The dramatic phase, the catastrophic stripping, the visible disruption of the body, the bright tail of falling matter, is hundreds of thousands of years away. We are watching, in real time, the early act of a play whose climax our species will not be alive to witness. That is a strange thing to know about a planet. We know how it ends. We know roughly when. We know what the end will look like in detail, because the physics gives us a model, and the model has been tested against other systems, and the answer is that, on a clock running for 3 million years, the planet falls into its star and is consumed. We know all of that tonight, with more certainty than we know almost anything else about WASP-12b. The end is, by some measures, the best characterized feature of the planet. Better characterized than its weather. Better characterized than its interior structure. Better characterized than its history. We do not, in the strict sense, know what the planet was made of when it formed. We know, with reasonable confidence, what its body will look like in 2.5 million years. The future is more legible than the past. That asymmetry, when you sit with it, is one of the more peculiar features of this kind of work. We tend to assume that we know more about what has happened than what is going to happen. In a system like WASP-12b, the relationship is reversed. The end is set. The past is murky. The model points forward more clearly than it points back. This is, mathematically, the standard shape of any process where the rate of change depends on the state of the thing being changed. It applies to radioactive decay in reverse. It applies to the melting of ice. It applies to the collapse of a dam, the toppling of a tree, the failure of a structural beam under increasing load. It applies to a great many of the slow catastrophes of physics. And it applies very precisely to the final orbital decay of a hot Jupiter into its star. Part 6. A trail of stolen air. There is a question that comes up when you look at the mass loss numbers that it is worth pausing on. Where does the stolen air go? Some of it falls directly onto the star. It is absorbed into the star's outer layers and adds very slightly to the star's mass, almost imperceptibly. The amount of WASP-12b's atmosphere that the star will eventually consume over the planet's entire lifetime is roughly the mass of one large Jupiter. The star, by mass, is about 1,000 times that. So even after the planet is fully consumed, the star will only have grown by about 0.1%. The eating is slow in cosmic terms, and the meal is, on the scale of the diner, a snack. Some of the atmosphere does not fall onto the star directly. It enters orbit around the star in a thin, diffuse disk and remains there slowly drifting before eventually being absorbed. There has been some evidence in sub-millimeter observations of the WASP-12 system by various teams over the last decade that such a disk may exist, although the evidence is debated, and the disk, if it is there, is much fainter than the planet itself. The point, for our story, is that the stolen atmosphere does not vanish. It moves. It transitions from being part of a planet to being part of a star on a time scale of months to years after it crosses the Roche limit. There has been, since the original Haswell and Fossati papers, a series of follow-up observations using both Hubble and ground-based ultraviolet instruments to refine the mass loss estimate. The numbers have shifted over the years, depending on which set of observations and which atmospheric model is used. Some teams have argued for higher loss rates, in the range of 10 to the -7 Jupiter masses per year. Others, using slightly different reductions, have argued for lower rates, closer to 10 to the -9. The difference, by a factor of 100, matters for the long-term picture, but not for the central conclusion. The atmosphere is leaving. It is leaving fast, by planetary standards. Whether the timescale for total atmospheric stripping is 10 million years or 1 billion, the planet is, in either case, on a clock. Here is the part that is worth pausing on, because it is one of those small moments of physics that becomes more remarkable the longer you sit with it. We are watching, in real time, from across most of 1,000 light years away, the slow death of a body that is roughly 400 times the mass of the Earth. Not by inference, not by theoretical extrapolation, by direct measurement. The atmosphere of WASP-12b on the night you are listening to this is in the process of leaving the planet. We can see the leaving. We can measure the leaving. We can quantify in tons per year how much air is being taken from the planet by the star. That kind of capability did not exist 20 years ago. It barely existed 10 years ago. It is, in the broadest historical sense, almost the newest kind of thing human beings know how to do. Watching planets die in real time across hundreds of light years with precision sufficient to publish the results in journals that physicists from 1,000 institutions can read has been a possibility for, generously, the last 15 years. It will continue to be a possibility and become an increasingly precise one for the rest of the century and beyond. We are on this kind of measurement in the very early days. The records we are setting tonight will be improved on, the numbers will be refined, the models will be sharpened, but the basic capability of looking at a planet's atmosphere across most of 1,000 light years and watching it bleed is now part of the toolkit. It will not go away. The next generation will inherit it and use it on more planets, and improve it and pass it on. There is a second question which is more subtle that physicists have been quietly arguing about since the mass loss was first measured. The mass loss is, on its own, not the fastest way for WASP-12b to be destroyed. At 10 million years to lose its entire atmosphere, that is a long time. Long enough that, if mass loss were the only mechanism in play, WASP-12b would persist, slowly diminishing, for many more generations of human civilization than have so far existed. But mass loss is not the only mechanism. There is a second one, much faster, much more decisive, and it has, since 2017, become the dominant effect in the planet's death. The second mechanism is the orbit itself. Part 7, 29 milliseconds per year. The orbit of WASP-12b is shrinking. Patra and his collaborators measured this very carefully by comparing the timing of transits over a period of about 10 years. Every transit, in principle, should happen on a perfect schedule. The planet's orbital period is fixed, the star's position is fixed, and the timing of one transit, given the timing of the previous one, should be predictable to within the precision of the measurement. If the transits start happening earlier than predicted, by tiny amounts, the orbit is shrinking. If they start happening later, the orbit is growing. Over the 10 years from 2007 to 2017, the transits of WASP-12b started happening earlier than the linear prediction. Not by much. The cumulative timing offset after a decade was about 3 minutes. But that was a robust measurement. It was not a fluke. It was reproduced in independent analyses by multiple teams, including a Polish astronomer named Gracjan Maciejewski and his collaborators at Nicolaus Copernicus University, who used additional ground-based observations to confirm the result. When the team converted the timing offset into a rate of orbital change, the answer was about 29 milliseconds per year. The orbit was getting shorter every year by 29 thousandths of 1 second. Here is the scale of that number. A millisecond is the time it takes a fast-moving sound wave to travel about 30 centimeters. The fastest a human can blink is about 100 milliseconds. The reaction time of a top-tier athlete is about 150. 29 milliseconds in human terms is the duration of a pulse of a hummingbird's wing. It is a fraction of a heartbeat. It is, on every scale you and I live at, irrelevant. But it is not irrelevant on the scale of a planet. WASP-12b's orbital period is just over 26 hours, which is, in milliseconds, about 95 million. The shift of 29 milliseconds per year against an orbit of 95 million milliseconds is 1 part in 3 million. Tiny. But it accumulates, year after year, century after century, millennium after millennium. And the rate, importantly, is not constant. As the planet falls closer, the rate increases. The eating speeds up. When you integrate the falling with its accelerating rate forward in time, the answer that comes out is that WASP-12b will reach the surface of its star and be entirely consumed in roughly 3 million years, not 3,000 years, not 30,000, not 300,000, 3 million. There was, between Patra's 2017 result and the eventual broader acceptance of orbital decay as a real phenomenon, a period of roughly 3 years. in which the field was, very quietly, divided. Some astronomers thought the decay measurement was robust. Others thought it might be a result of something called apsidal precession, which is a different effect that can also produce changing transit times, but for entirely different physical reasons. In apsidal precession, the orbit of the planet itself does not shrink. Rather, the orientation of the orbit in three-dimensional space slowly rotates, and the transits, which occur at one specific orientation, drift in time without the planet actually getting closer to the star. The two effects on a transit timing diagram look very similar in the early data. They diverge slowly over time, but you need years of measurements to tell them apart cleanly. The Patra paper acknowledged this ambiguity. It presented the orbital decay as the more probable explanation, but did not rule out apsidal precession entirely. The decision between the two interpretations would, the paper said, require more data. In 2020, an astronomer named Samuel Yee, then at Princeton University, working with his thesis advisor, Joshua Wynne, used additional observations from the TESS satellite, the Transiting Exoplanet Survey satellite, to confirm the orbital decay independently. The TESS observations, taken with a different instrument with different systematics on different dates, agreed with the original Patra result. The orbit was shrinking. The rate was about 29 milliseconds per year. The planet was, in fact, falling. That confirmation made WASP-12b the first exoplanet for which orbital decay had been measured robustly, with multiple independent confirmations in real time. Other hot Jupiters have since shown evidence of decay as well. Kepler 1658b, an older system, has decay even faster than WASP-12b's. But WASP-12b was the first. It was and is the test case for what happens to a planet when its orbit, for reasons we are still working out, decides to come apart. Part 8. Why the orbit is failing. The reason WASP-12b's orbit is shrinking is, in its physics, both subtle and simple. The shrinking comes from a process called tidal dissipation. To understand it, you have to picture the system as a pair of bodies, the star and the planet, exchanging energy through their mutual gravity in a way that gradually pulls them together. Every body that has tides on it loses energy. The Earth has tides on it, mostly from the Moon. As the Earth rotates, the tidal bulges in its oceans, raised by the Moon's gravity, are dragged slightly forward of the Moon's position by friction with the seabed and with the rotating Earth itself. The friction is very slight, but over geological time it transfers energy very slowly from the Earth's rotation to the Moon's orbit. The Earth's rotation slows down by a tiny amount every century. The Moon's orbit grows by about 3.5 centimeters per year. The system is, very gently, being pulled apart. For WASP-12b, the same process is happening, but in reverse and faster. The tidal bulges raised on the star by the planet's gravity are dragged slightly behind the planet's orbital position by friction inside the star itself. That friction transfers energy from the orbit to the star rather than the other way around. The orbit loses energy. Energy in an orbit is conserved by the orbit shrinking. So, the orbit shrinks, the planet falls inward, and the falling, paradoxically, makes the planet move faster, even as the orbit gets smaller, because closer orbits have higher orbital velocities. The amount of friction inside a star in this calculation is captured by a single dimensionless number, called the Q parameter. Q stands for the quality factor of the tidal dissipation. A high Q means the star dissipates orbital energy slowly and the orbital decay is slow. A low Q means the star dissipates fast and the decay is fast. Q for the Sun in its present state is enormous, of the order of 10 million. The Earth's orbit is not, in any practical sense, decaying because of the Sun. Q for WASP-12, when Patra and his collaborators worked it out, is much lower, somewhere around 200,000. That is roughly 50 times more dissipative than the Sun. It is, in fact, more dissipative than most theoretical calculations had predicted any star should be. Here is the part that is still being worked out. Why is WASP-12 so dissipative? What is happening inside the star that makes it lose orbital energy 50 times faster than expected? Several models have been proposed. Some involve resonance between the planet's orbit and the star's internal oscillation modes. Some involve subsurface convection patterns. Some involve the star being slightly more evolved, slightly older, slightly more prone to tidal coupling than its surface temperature would suggest. None of these models is yet definitive. The question of why WASP-12 is eating its planet so quickly is, at the time of this telling, genuinely open. What is not open is that it is happening. The orbit is decaying. The rate is 29 milliseconds per year. The planet has, on the most current models, about 3 million years left. There is a deeper question buried inside the dissipation problem which is worth a brief note before we move on. The Q parameter, the dimensionless measure of how much friction a star applies to its tides, is not just a single number. It depends on the frequency at which the tides are being raised. A planet in a tight orbit raises tides at a high frequency. A planet in a wide orbit raises tides at a low frequency. The dissipation inside any given star is not the same at every frequency. There are resonances, places where the star's internal oscillation modes happen to match the frequency of the tide, and at those resonances, the dissipation can be enormously stronger than it would be elsewhere. WASP-12b, by some interpretations, may simply have the bad luck of orbiting at exactly the right period to drive an internal resonance inside its star. Most hot Jupiters do not. The ones that do fall faster than the ones that do not. This means that the rate of orbital decay we measure on WASP-12b may not be a universal fate for hot Jupiters. It may be the fate of some hot Jupiters, the unlucky ones whose orbital period happens to land on the wrong place in the spectrum of stellar oscillations. The lucky ones whose periods land between resonances may decay much more slowly, on timescales of hundreds of millions of years rather than tens of millions. The galactic population of hot Jupiters may be sorted very slowly by which ones happen to drift into the resonance bands first. The unlucky ones are eaten. The lucky ones persist. If that is the right picture, then WASP-12b is, in a real sense, a victim of its own orbital geometry. The orbital period of one Earth day and a few minutes is, by some accident, the wrong period for this particular star. A slightly longer orbit would have meant a much slower decay. The planet would have lived for hundreds of millions of years more. As it is, the period is what it is, the resonance is what it is, the dissipation is what it is, and the timeline is 3 million years. The randomness of that, when you sit with it, is a kind of cosmic joke. The thing that determines the death of a planet in this picture is not anything about the planet itself. It is the accident of where its orbit happens to fall in a spectrum that has nothing to do with the planet at all. 3 million years sounds like a lot. From the planet's perspective, it is. It is more than the time since the first humans walked upright. It is more than the time since modern Homo sapiens existed. It is many, many times longer than all of recorded human civilization. But on the scale of the system itself, it is, almost by any measure, the very last chapter. WASP-12, the star, has been around for roughly 2 billion years and will live for perhaps another 5 or 6. WASP-12b, the planet, has been there for roughly the same. 3 million years out of those billions is, in proportion, the last few minutes of a long film. The planet's death is, by cosmic standards, imminent. Part 9. What the death looks like. Modelling what will actually happen as WASP-12b falls is, in some ways, the most fascinating part of this story, because it is one of the few cases in astronomy where the death of an entire planet has been calculated in detail in advance. For the next 2.5 million years, the basic picture is what is happening now, but accelerating. The orbit shrinks, the planet falls closer, the Roche limit shifts inward and the planet eventually crosses it. Once it crosses, the tidal stripping becomes catastrophic. The atmosphere is no longer being slowly bled away from a near side bulge. The whole upper atmosphere is being torn off, layer by layer, on every orbit. The planet's body becomes increasingly disrupted. The egg shape becomes more pronounced. The teardrop becomes more elongated. The tail of stripped material, the stream falling from planet to star, becomes wider, denser, brighter. In the final few 100,000 years, the planet's structure begins to fail. The hydrogen and helium that make up most of its mass are, by then, being stripped at rates that exceed the planet's ability to retain its shape. The dense interior is exposed. The hot core, which had been buried under hundreds of kilometers of compressed atmosphere, becomes the visible outermost layer. The planet, in shape, has by then ceased to be a planet at all. It is a stretched, shrinking, glowing knot of hot matter held together by what is left of its own gravity, tracing a tightening spiral around its star. In the final 10,000 years, the spiral becomes very tight. The orbital period drops from a day to 12 hours to 6 to 3. The planet is no longer, in any meaningful sense, a separate body. It is a stream. It is matter being fed in a continuous current from a source point that is itself being compressed and consumed into the surface of the star. In the final months, the source point disappears. The remaining mass of the planet plunges into the star's outer layers. There is, in some models, a brief flare, a few thousand years' worth of stellar brightening, as the absorbed material releases its gravitational energy in the form of heat and light. Here is the part that is easy to miss. The flare, when it happens, will not be cataclysmic. It will not be a supernova. It will not destroy anything else in the system. The star, which is 1,000 times more massive than the planet, will absorb the planet's mass with very little visible reaction. The brightening, by some estimates, will be perhaps a few % over the star's normal output, sustained over a few thousand years, before settling back. To anyone outside the system, watching with a careful instrument over a long enough baseline, it will look like a gentle flicker, a small, slow swelling and dimming. The eating, when it finally completes, will be the kind of event that the universe absorbs without any drama at all. It is the slow part, the 3 million years before the final plunge, that is genuinely unusual. What this means is that if you were to be present, hypothetically, in a hypothetical observation post that could persist across geological timescales, watching WASP-12 from somewhere safely outside the system, you would not, on most days, see anything dramatic happening. The star would look the same as it always did. The planet, when it transited, would dim the star by the usual 1.5% for the usual 3 hours. The orbital period would tick down 29 milliseconds at a time, year after year, in a way that would be invisible without a precision clock. Almost nothing about the experience of watching from the outside would feel like watching a planet die. It would just feel like watching a planet in a tight orbit around a star, doing what it has always done. The death is in the data, not in the spectacle. You would have to look at the numbers with care over decades to see what was actually happening. That is, in many ways, the most quietly devastating thing about this kind of cosmic process. The disasters of astronomy are not, on the whole, dramatic. They are slow, they are calm, they happen very gradually on instruments that need decades to read them, and the universe itself does not register them as disasters at all. They are just, as far as the physics is concerned, the working out of standard laws. The planet falling into the star is, to the star, no more remarkable than a leaf settling on a lake. The star is going to live for billions of years more. The planet is, by then, just a small contribution to the slow churn of stellar interior chemistry. The star, briefly, would shine more brightly. Anyone watching from many hundreds of light years away with a sensitive instrument would record a bump in the light curve. The bump would last a few thousand years. Then it would fade. The star would settle back to its previous brightness. The planet by then would be entirely gone. The atoms that had once made up its atmosphere and its mantle and its core would now be part of the star's atmosphere, part of the star's mantle, part of the star's slow internal mixing. There would be no trace anywhere in the system that a planet had ever been there. 3 million years from now, give or take, that is what is going to happen. The light from the brief flare when it eventually leaves WASP-12 will take 870 years to reach Earth. Whoever is here then, if anyone is here, will see, very faintly, in their instruments, a brief brightening of a faint yellow star in the constellation Auriga that lasts for a few millennia and then fades. They will know, if they have kept the records, that they are watching the moment a planet died. We will not be alive to see it. The astronomers who first measured the decay will not be alive. Their students will not be alive. The species we are will, almost certainly, no longer exist in its current form. 3 million years is not a human timescale, it is a planetary one. We are inside the early part of the story, not the late part. The death will happen with or without us on the schedule the orbit has set. Part 10. We are not the only one. Here is a thing that is worth pausing on. WASP-12b, although it was the first hot Jupiter for which orbital decay was definitively measured, is not the only one. It is, increasingly, looking like the first of a category. Kepler 1658b, an older star with a similarly close-in giant planet, was shown by a team at Harvard in 2022 to be decaying as well. The orbital period of Kepler 1658b, the team showed, is shrinking by about 130 milliseconds per orbit, which is several times faster than WASP-12b's rate. The planet has, on the best models, perhaps 2.5 million years before it is entirely consumed. Several other hot Jupiters in surveys done over the last few years are showing tentative signs of decay. The number is growing. The pattern is consistent. Hot Jupiters, the kind of close-orbiting gas giants that SuperWASP and Kepler and TESS have been finding by the dozens over the last 15 years, are not stable on long timescales. They are, in a real sense, the doomed planets of the galaxy. They are spiraling in, they are being eaten. Some of them are nearer the end than others, but they are all, every one of them, in the process of falling. The total number of confirmed hot Jupiters at the time of this telling is somewhere around 500. The total number of likely hot Jupiters, including unconfirmed candidates, is somewhere around 1500. If the rates of orbital decay measured for WASP-12b and Kepler-1658b are typical, even approximately, then a meaningful fraction of those hot Jupiters are currently being eaten on timescales of millions to tens of millions of years. The galaxy, in other words, is full of slow consumption events. We have been measuring planets for 30 years. We have, in that time, found at least 2 clear cases of planets being eaten in real time. The rest, when we go back and measure them carefully enough, will probably show similar patterns. Here is the implication that nobody has yet been brave enough to put bluntly in a paper, although several people have hinted at it in conferences. If hot Jupiters are uniformly decaying on the time scale of a few million to a few 100 million years, and we are still finding so many of them today, then either the rate of formation of hot Jupiters is high enough to compensate for the rate of consumption, or we are observing the population at an unusually rich moment in galactic history, or some combination of the two. The first possibility, that hot Jupiters are constantly being made, raises the question of how. The second possibility, that we are at a special moment, raises the question of why. Neither has been resolved. Both are open. What is not open is that the eating throughout the galaxy is going on. WASP-12b is one example. Kepler-1658b is another. There are almost certainly hundreds more in the data we already have, waiting for the precision timing follow-up that will reveal them. This is not, in the strict sense, a recent finding. Hot Jupiters were always, by the simplest physical models, expected to be migrating inward. The original theoretical work on this was done in the 1990s by a trio of astronomers named Doug Lynn, Peter Bodenheimer, and Derek Richardson, who showed that gas giants formed far from their stars could, under various circumstances, migrate inward through the protoplanetary disk and end up in close-in orbits. The migration mechanism they proposed was different from the late-stage tidal decay we are now measuring, but the underlying picture of hot Jupiters being unstable bodies that are constantly losing energy to their stars was already in the literature. What is recent is the measurement. Until 2017, no one had ever caught a single planet anywhere in the act of falling. The theoretical predictions were one thing. The actual observation of an orbit shrinking in real time on a particular planet was another. Patra's paper and Yi's confirmation and the Polish reconfirmation and the TESS data made the abstract concrete. The hot Jupiter death rate is no longer a theoretical number. It is a measured one. I'm not saying that every hot Jupiter is dying as fast as WASP-12b. I'm not saying that the rate of orbital decay we see in this one system applies to every other system. I'm not saying that the 3 million year timeline is the standard fate of every gas giant in the galaxy. What I am saying is something quieter than that. What I am saying is that the picture in the early days of exoplanet astronomy, of stable solar systems with stable planets in stable orbits, is increasingly being replaced by a different picture. A picture in which planets, and especially close-in giant planets, are not permanent. They are temporary. They are formed. They migrate. They spiral. They are eaten. The galaxy, when you look at it carefully, is not a collection of permanent worlds. It is a flow, a slow, hot, gravitational flow of matter from planet to star and back again on timescales we are only now beginning to measure. WASP-12b is one current, there are many others. The eating is, throughout the galaxy, ongoing. Part 11. The end of every solar system. Here is where the story leaves WASP 12b for a moment and goes somewhere closer to home. Every star in the galaxy, including our own, will eventually go through changes that consume some or all of its planets. The mechanisms differ from system to system. Hot Jupiters like WASP 12b are eaten by tidal decay before their stars have aged significantly. Cooler planets in wider orbits around stars like our own Sun will be eaten in a different way. They will be eaten when the star itself, near the end of its life, expands. Our own Sun is about 4.5 billion years old. It is, by every reasonable model, about halfway through its main sequence lifetime. 5 billion years from now, give or take, the Sun will have used up most of the hydrogen in its core. The fusion that has been keeping it stable for the last 10 billion years will start to fail. The core will contract. The outer layers, in response, will expand, and in the process of expanding will cool slightly and turn from yellow to orange to red. The Sun will become, over a few 100 million years, what astronomers call a red giant. When the Sun is a red giant, it will be enormously larger than it is today. The radius will swell to roughly the orbit of the Earth. The Earth itself by then will probably have already been engulfed. Mercury will be gone, swallowed, much earlier in the expansion. Venus will be gone shortly after Mercury. Earth will be gone or just barely surviving in a much altered orbit. Mars, depending on which model you trust, may survive, but as a charred remnant of its former self, with no atmosphere, no oceans, no possibility of any kind of life. In the language of WASP 12b, the inner planets of our solar system will be eaten, not over 3 million years, the way a hot Jupiter is, over a few 100 million in a much slower, much more gradual swelling of the star. But the result is the same. The atoms that, at this moment, make up Mercury and Venus and possibly the Earth will, in 5 to 7 billion years, be part of the Sun's outer layers. They will be cycled through the star's interior, briefly, before the Sun's death throes throw most of its mass back out into the galaxy as a planetary nebula, and the star itself contracts into a white dwarf. There is a thought experiment that astronomers sometimes do when they want to put the death of WASP 12b into context. Imagine that instead of being an unrelated planet around an unrelated star, WASP 12b were a probe sent into our future, a kind of preview of what is going to happen to our own innermost worlds. The clock would be different, the mechanism would be different, but the basic shape of a planet's atmosphere being stripped, of the body being engulfed, of the atoms being incorporated into the star, would be the same. We are in some sense watching in WASP 12b a very fast version of what will eventually happen here. The star is the same kind of star. The planet, in proportion to its star, is in the same kind of intimacy. The eating is the same kind of eating. The clock is just running faster on this particular world by a factor of a few thousand. That is not, on its own, a comfortable thought, but it is, when you sit with it, also not the kind of thought that leaves you nowhere to stand. The Earth, on the time scale of stellar evolution, is mortal. The species that lives on it on the time scale of any individual life is mortal. The individual life on the time scale of an evening like this one is a very, very brief flicker, and yet, on the same evening, all of those things are also intact. The Earth is here, the species is here, you are here, listening. The mortality, in cosmic terms, does not arrive tonight. It does not arrive next year. It does not arrive in your lifetime or in your great-grandchildren's lifetime, or in any lifetime that any human being currently being born will experience. The eating is real. It is also, for our purposes, a long way off. WASP 12b is in some sense the rough draft of our own ending written by the same physics on a faster clock. The thing the rough draft can teach us more than anything else is patience. The death of a planet, even on the fast clock, takes longer than civilizations last. The death of a planet on the slow clock takes longer than species last. There is no version of this in which the eating happens quickly enough to be a personal problem. It is, structurally, beyond any particular individual's horizon. Every planet in every solar system has an ending. Hot Jupiters end in 3 million years. Inner rocky planets in sun-like systems end in 7 billion. Outer planets in those same systems sometimes survive into the white dwarf phase, drifting in increasingly distant orbits around a small, dim corpse of a star. A few survive even longer. None survives forever. That is, in many ways, the strangest thing about WASP 12b. It is not, at the level of physics, a special planet. It is just an early example of a fate that, sooner or later, applies to almost every planet in the galaxy. WASP 12b is, in a real sense, a preview, a worked example on a faster clock than ours of what is going to happen here, on a slower one. Part 12. We did not always know this. We did not always know that planets ended. For most of human history, the planets, by definition, were the things that did not change. The fixed stars were fixed. The wandering stars, the planets, wandered, but they wandered along the same paths, year after year, century after century, on the same predictable schedules. The planets, in every culture that had them, were associated with permanence, with cycles, with the kind of slow regularity that you could, if your culture cared to, build calendars and rituals around. That picture lasted more or less until the 17th century, when Newton's gravity replaced the Aristotelian celestial spheres with a model in which the planets were just rocks falling around the sun under one universal force. Even then, the picture was static. Newton's solar system was permanent. The orbits in his calculations did not change. Every planet would, in his physics, move forever along its prescribed ellipse, unless something else perturbed it. In the 18th century, the picture got slightly less permanent. Joseph Louis Lagrange and Pierre-Simon Laplace, working out the gravitational interactions between planets, showed that the orbits of the inner solar system are not, in fact, permanent. They are, on long enough timescales, chaotic. Mercury's orbit, in particular, is unstable. Over the next 5 billion years, there is a non-trivial probability that Mercury will be ejected from the solar system entirely by gradual gravitational interactions with Venus and Jupiter. The probability is not high, perhaps 1 or 2%, but it is not zero. Mercury, like WASP 12b, has an end. In the 20th century, with the discovery of stellar evolution, the end of every star and the consequences for its planets became part of the standard picture. The Sun's red giant phase, Earth's eventual engulfment, Mars's possible survival, the white dwarf future. By the time the first exoplanets were discovered in the 1990s, astronomers already knew, in principle, that planets did not last forever. The slow change in this picture, from a static cosmos to a dynamic one, is one of the more remarkable intellectual transformations of the modern era. Most people, even people who think about science casually, still carry around a picture of the universe that is roughly Newtonian. The planets go around the sun goes around the center of the galaxy. The galaxies sit, more or less, in their current arrangement and have done so for a long time and will continue to do so for a long time. That picture is, for most everyday purposes, accurate enough. But in the strict sense, on long enough timescales, almost none of it holds. The planets are not eternal. The sun is not eternal. The galaxy itself is not eternal in any strong sense, because it is going to merge with Andromeda in about 4 billion years and end up as a single, larger, fundamentally different object. Even the universe on the longest timescales we have any evidence for is not stable. It is expanding. The expansion is accelerating. The galaxies, billions of years from now, will recede from each other so fast that no light will be able to cross between them, and any observers in any of them will, in their distant future, see a sky that is empty except for the few hundred galaxies in their own gravitationally bound cluster. Everything, on long enough time scales, is in motion. Everything is being undone by some slow, patient process, even as it is being made by another. The picture of the universe as a stable furniture arrangement is wrong at every level. It is not a furniture arrangement. It is a flow. Stars form. Planets form around them. Planets migrate. Stars age. Planets fall. Stars expand. Planets are eaten. Stars die. Planets, the survivors, drift in increasingly distant orbits around increasingly cold corpses. New stars form from the dust of the old ones. The cycle at the level of the galaxy does not stop, but at the level of any individual system it has a finite number of acts. WASP-12b is in the closing act of its own particular play. Other systems are in earlier acts. Some are still in the first scene. Some, like our own sun and its planets, are in the long second act, the part of the play where everything appears stable, but which is, when you look closely, also moving very slowly toward the curtain. The curtain is real, it is just very far away. What they did not know until 2017 was what the early stage death of a hot Jupiter looked like in real time, in detail. The Patra paper and the work that has followed it gave us the first direct view of that process. It is one thing to know in principle that planets eventually end. It is another thing to watch one bleeding into its star every 26 hours on a measurable schedule in real time from across most of 1,000 light years away. We, the species that lives in this universe, have just barely arrived at the level of instrumentation where we can see this. We are not, in any sense, the first. There have been other intelligent species, almost certainly, in other parts of the galaxy at other times. Some of them may have built better instruments than we have. Some of them may have watched their own system's equivalents of WASP-12b being consumed. We are, in our local stretch of cosmic time, only the most recent observers of a phenomenon that has been visible in principle since the galaxy formed. But it is being visible to us now. That is what changes. We are alive in the first generation of human beings that has watched a planet die in real time. The data is on hard drives in offices in Massachusetts and New Jersey and Poland and Geneva. The papers are in journals you can read online. The orbital measurement, the mass loss measurement, the decay rate, the 3 million year timeline are all today available to anyone who wants to look. That is, when you sit with it, an extraordinary thing to know about your own moment. Part 13. The View from Far Away. Here is a thought that I sometimes sit with when I read about WASP-12b. The light from the planet's eventual destruction, the brief flare when its mass plunges into the star, will leave the WASP-12 system roughly 3 million years from now. It will then take 870 years to reach Earth, travelling at the speed of light through the empty space between stars. By the time it arrives, our species, if it still exists in any recognizable form, will have lived a further 3,870,000 years beyond this moment. That is more time than separates us from our common ancestors with chimpanzees. The civilization that observes the flare, if any civilization does, will not be the civilization that first measured the decay. They will not be related to us except through whatever long thread of inheritance has carried whatever consciousness our species possesses into theirs, but the photons will arrive. The flare, when it leaves WASP-12, will cross the galaxy at the speed everything crosses the galaxy at, and a tiny fraction of its light, a few photons, will reach the Earth and will fall on whatever instrument is pointed in the direction of Auriga at the right moment. Whoever sees them, on whatever instrument, on whatever evening, will see the death of a planet that was by then 4 billion years old and that died slowly on a measurable schedule in a process that began long before any of them was born. There is something, I think, very calming about that. The death of WASP-12b is not a tragedy in any human sense. It is a process, a long, slow, predictable, measurable process that takes longer than any of the witnesses to it will be alive to see. The planet does not suffer. The planet, as far as we can tell, has nothing on it that could suffer. There are no oceans, no continents, no surfaces, no biospheres, no organisms of any kind that the eating is destroying. The day side of WASP-12b is hotter than the surface of an industrial furnace. The atmosphere is a turbulent, ionized, partly vaporized mass of hydrogen and helium and trace metals. There is no life on this planet. There never was, there never will be. The eating is happening to a body that is, in every meaningful biological sense, already empty. That distinction matters. When we contemplate the death of an inhabited world, the meaning is different. The Earth, in its eventual fate, is a different kind of story, because the Earth currently has, on its surface, an entire biosphere of cells, plants, animals, organisms of every conceivable kind which would not survive the kind of process that WASP-12b is undergoing. The death of an inhabited planet is, in a way that has no analogue in human history because no human has ever seen one, a moral event. The death of an uninhabited planet is a physical one. WASP-12b is the second kind. There is no biosphere on it that we would mourn. There is no civilization on it that we would lose. The eating is happening to a body that is, by any reasonable definition, already a corpse, just one that has not yet finished arriving at the place corpses go. This is, in a way, a kind of permission to look at the eating without the heaviness that would otherwise come with it. We can study WASP-12b's death in detail on a million-year clock, with the calm attention of a researcher rather than the grief of a mourner. The planet is a worked example. It is not a tragedy. The processes it shows us are the processes that will, in time, work themselves out on inhabited worlds as well. But on WASP-12b itself, the only thing being lost is matter, and matter, in the universe, is not lost. It is moved. The star does not gain in any meaningful way. The atoms, when the eating is done, are still atoms, just in a different arrangement. The information which we measure tonight will continue to propagate outward, through the spectrum of the star, through the timing of its transits, through the very slow drift of its catalogue position, until the system is consumed and the consumption itself becomes a new data point for whoever is watching at that future moment. There is a small mental exercise that I find useful when I think about deep time astronomy. Imagine that instead of an evening on Earth in our own century, you were dropped into the same evening on the same Earth, but 2,500 years ago. The stars in the sky would be very nearly the same. The constellation patterns would be recognizable. Auriga would still be there in the winter sky, with Capella as its brightest star. WASP-12 would still be in its position, indistinguishable to the naked eye, much too dim to see. The planet would still be orbiting every 26 hours with its egg shape, with its hot atmosphere, with its slow leak. The whole story would be unfolding then, exactly as it is unfolding now, on a planet none of the people of that era had any conception of, around a star none of them had any name for, in a system whose existence was beneath the threshold of anything any of them could detect. 2,500 years from now, the stars in the sky will still look very nearly the same. The constellation patterns will be recognizable. WASP-12 will still be in its position. The planet will be slightly closer to its star than it is tonight. Its atmosphere will be slightly thinner. The orbital period will be about 1.25 minutes shorter than it is now. The story will still be unfolding. Whoever is here in that distant century will have access to instruments we cannot yet imagine, and will be able to read details in the spectrum that we cannot yet read. They will know things about WASP-12b that we do not know. They will have refined the timeline, sharpened the death model, perhaps even seen the early stages of the catastrophic stripping. They will be part of the same chain that we are part of now. We are part of a long chain of observers. Some of them came before us, although none of them on Earth came before us with the instruments we now have. Some of them will come after. The data we are gathering tonight on WASP-12b is being added to the slow, patient record of how planets end, and that record will continue to be added to by people we will never meet, on instruments we will never see, until the question of how planets end is no longer an open one. By then, on a clock most of us will not live to see, the planet itself will probably be gone. The data will still be here. Part 14, Coming Home. We did not set out to find this, we set out to find planets at all. The Super WASP survey was, in 2004, one of the early experiments in detecting transits. The cameras were small, the team was small, the expectation was that they would find a few hot Jupiters, write a few papers, advance the field by an inch or two, and move on. Nobody, in 2008, when WASP-12b was first detected, expected that the planet would turn out to be the first ever exoplanet caught in the act of dying. The death, like the planet itself, was a side discovery, a bonus on the way to other things. That is, in many ways, the deepest pattern of this entire field. We do not, as a species, set out to find what we eventually find. We set out to count. We set out to measure. We set out to refine techniques that other people built before us. And in the process, in the slow accumulation of careful measurements, we sometimes notice, almost by accident, that something we had assumed was permanent is not. That something we had assumed was stable is, in fact, in the very process of coming apart. That something we had assumed had nothing to do with us has, on closer inspection, a great deal to do with us, because the same process is going to happen on a longer clock to our own home. WASP-12b is being eaten. The eating has been going on for a long time. The eating will go on for another 3 million years before it ends, and then it will be done, and the system will be quieter than it is now, and a star whose planet was famous, briefly, in our generation of astronomers, will be just one more star in a very large catalogue. No one in the long run will remember WASP-12b. No one will write its biography. No one will visit its site. The data will sit in the papers, and the papers will sit in the journals, and the journals will sit, increasingly, in databases that are, themselves, kept alive by people who do not necessarily remember why they were originally created. But the eating is happening tonight. The atmosphere on the near side is, at this moment, drifting toward the star, in its long, thin tail, on its slow, patient current. The orbital period between this orbit and the next is 29 milliseconds shorter than it was a year ago. The planet, which is too far away to see and too small in its silhouette to imagine, is, in some real sense, in the process of disappearing by tiny increments every day on a schedule we have measured. You can let it go for tonight. The eating does not need your attention. It is happening with or without you. The star is doing its slow, patient work. The planet is doing what planets eventually do. The orbit is shrinking and the spiral is tightening, and the photons that carry the news will keep arriving on Earth, on the instruments of whatever generation is here to read them, until there is no more news to send. There is, I think, a kind of comfort that comes from understanding processes that are bigger than you. Most of the difficulties of an ordinary life are, by their nature, on a human scale. The deadlines that frighten you, the conversations you have not had, the worries that will not let you sleep, are, almost without exception, problems that can be solved or absorbed or moved past on a time scale of days or weeks, or at the very most years. The size of the trouble matches the size of the life it is troubling. The eating of WASP-12b is on a different scale. The star will not be persuaded to stop. The planet will not be saved. The orbit will not be reversed. None of the things that, at a human scale, would normally come into play, even apply here. The process is happening because of the laws of physics on a body the size of Jupiter, around a star the size of the Sun, 870 light-years from Earth. There is nothing you or any human being can do about it. There is nothing anybody, individually or collectively, will ever be able to do about it. It is just happening. That kind of helplessness, when you sit with it, is not a problem. It is the opposite. It is a release. The kind of release that comes from finally understanding that some things are not your responsibility. The eating is not something you have to fix. The eating is something the universe is doing on its own schedule, in its own way, with its own patience, regardless of whether anybody's watching. The astronomers who have given their lives to measuring it are not trying to stop it. They are trying to understand it. The work is observational. The work is calm. The work continues every night on instruments around the world, because the universe is still there doing what it has always done, and a small number of human beings still find that fascinating enough to spend a career on. You can join them, for tonight, in the quietness of that fascination. You do not have to fix the eating. You do not have to feel anything about it except whatever you naturally feel. You can simply, in the way you would listen to any long, calm story, let the story unfold and trust that it will land where it is going to land on its own schedule, whether you stay awake to hear the end or not. You can let it go for tonight. The constellation Auriga is in the winter sky in the northern hemisphere between Taurus and Gemini, near the bright star Capella. The shape of the constellation, depending on which star chart you use, is sometimes drawn as a charioteer holding a goat. The Greeks said it was Erichthonius, the legendary king of Athens, who was said to have invented the four-horse chariot, placed in the heavens by Zeus. The Babylonians called it the chariot of Marduk. The Egyptians associated it with the goddess Hathor. Almost every civilization that paid attention to the night sky drew this same pattern of stars and built a story around it. WASP 12 is not visible to the naked eye. It is far too dim. The magnitude of the star is around 11.6, which is more than 400 times fainter than the dimmest star you can see without help. To find it, you would need a small telescope, a star chart that knows exactly where to point, and a clear sky. Most of the people who have ever lived have never known it was there. Most of the people who will ever live, even with much better equipment than we have now, will never see it personally. It is, by every standard of human attention, an obscure star. But it is there. Around it every 26 hours a gas giant the shape of an egg is making a slow, hot, doomed lap of its star. The lap has happened from the planet's birth to tonight, more times than you can count. The lap will happen before the end, more times still. But not infinite times. The number is, finally, finite. The eating has a clock on it. The clock is running. The galaxy, as far as we can tell, contains many such clocks. Some are running fast, like WASP 12b's. Some are running slow, like our own suns. Some are barely running at all, having reached the kind of stable middle age in which not very much will change for billions of years yet. The clocks are everywhere. The eating is happening in some form around almost every star, on a time scale appropriate to that star and its planets. We have learned in the last 20 years how to read some of them. We will learn in the next 20 how to read more. Tonight, in Auriga, the eating goes on. The orbit ticks down by a tiny fraction of a millisecond every hour. The atmosphere drifts off the near side bulge in its long, thin tail every orbit. The star takes back into its outer layers the matter that had been part of the planet for the 4 billion years before tonight. Nothing is hurried. Nothing is panicking. The processes are running on their own schedules with their own patience, regardless of whether anybody is watching. The astronomers are still at their instruments. The next observation will refine the rate. The next paper will sharpen the timeline. The next generation will inherit the data and add to it. The eating will continue into a future that runs longer than any of us, until the planet is finally gone and the system is quieter, and the work, by then, has moved on to other planets, around other stars, in other constellations, doing the same kind of slow, patient work that this small story has been about. For tonight, you can let the eating be. It does not need you. The galaxy does not need you. The universe does not need you. You can put down the day and rest, and trust that the slow, patient work of the cosmos will continue on its own clock while you sleep. And around it, every 26 hours a gas giant the shape of an egg is making a slow, hot, doomed lap of its star. The lap has happened from the planet's birth to tonight, more times than you can count. The lap will happen before the end, more times still, but not infinite times. The number is finally finite. The eating has a clock on it. The clock is running. 3 million years from now, the orbital period will be shorter than it is today. The atmosphere will be thinner, the egg shape more pronounced, the trail of strip material denser. By every measurement we know how to take, the planet, 3 million years from now, will be on the cusp of its final fall. The astronomers of that future epoch, if there are any, will be watching the spiral close. They will be doing what we cannot do. They will be seeing the end. We will not see the end. We will see, in our own data, the slow build-up, the hundredth of a second per year orbital decay, the atmospheric stripping, the Lyman alpha tail, the sub-millimeter disk, the slowly falling photons from a yellow star 870 light-years away, carrying their tiny chemical message every night, on every clear winter evening, through the constellation Auriga, onto whatever instrument is pointed at them. We will see the early chapters of a story whose closing chapter will be read by people who do not yet exist, on instruments that have not yet been built, in a language that has not yet been written. That is, perhaps, the most quietly beautiful thing about this kind of work. The story is longer than any individual reader. Each generation reads a chapter and adds a chapter. The whole book, when it is finally finished, will not have a single author. It will have thousands. Most of them will be people you have never heard of. Most of them will not themselves ever be famous. They will simply have done the work in their own time, on their own instruments, and passed the work along. The star is still feeding tonight. The planet is still mostly there. The orbit is still tightening. The next observation will refine the rate. The observation after that will refine it further. Across the rest of the century, the picture will sharpen, and the timeline will become more certain, and the death of WASP 12b will become, in the catalogues, a known quantity, with an estimated date attached, give or take a few 100,000 years. You can rest for tonight. The eating will continue. The galaxy is full of slow, patient consumptions, of which this one is just the first we have caught in the act. The astronomers are still at their instruments. The orbit is still tightening by 29 milliseconds every year. The story is, at this moment in its early chapters, the end, when it comes, is a long way off. Good night. Sleep well. The star is still feeding. The planet, for tonight, is still mostly there.